lecture. This is from 4.2 lecture. So though we covered the material, which is basically the basic idea of the VSEPR shapes, which are the tetrahedral, trigonal pyramid, and bent. We're going to get to put this into practice. So this is a recipe, as I mentioned, where you look at the Lewis structure. So the Lewis structure is the two-dimensional on paper, how the atoms are bonded. So looking at the Lewis structure, the two-dimensional, you can use the two-dimensional to figure out the three-dimensional shape. That's called the VSEPR shape. And it's based on VSEPR theory, which is that you have a central atom. So your molecule has a central atom, and that central atom will be surrounded by some bonds and or lone pairs. So you will have these bonds or lone pairs are a maximum of 4. So you can have 4 bonds. You can have some combination of bonds and lone pairs, like 3 bonds and 1 lone pair. But you will have a maximum of 4 things that are stuck around your central atom. Okay, so you have a central atom and 4 things around it. And these electron pairs can be bonding pairs or lone pairs. So the lone pair, remember, are non-bonding electrons. So an example is the water molecule H2O is an oxygen which has a hydrogen on either side, and those are bonds. Those are the bonding pairs of electrons. So that's 2 electrons in that bond, 2 electrons in that bond. And then there are lone pairs, which are the electrons that are just dots. They're always going to be in pairs when you have a molecule that's stable. And those dots mean that those are lone pairs. They are electrons that are pairs that are not in bonds. So they're called non-bonding electrons. So the electrons and the bonds and the lone pairs, they all are stuck to the central atom and they want to be as far away as possible. So they repel, okay, because they're all negatively charged, whether the electrons are in bonds or in lone pairs. And they need to move around and still be stuck to the central atom. And so these are recipes for the 3-dimensional molecule shapes. And that's what VSEPR theory is. So it predicts the 3-dimensional molecule shapes, okay, which are these main shapes. Now there are more than these main shapes, but there are 1, 2, 3, 4, 5 VSEPR shapes. And you predict the shapes by looking at the recipe, which is how many bonds and how many lone pairs on the central atom. So that's what this table is when you have 4 bonds to a central atom, it's going to be a tetrahedral shape. Okay, the tetrahedral is the tall pyramid, or the tripod that I showed you last time. When you have just 3 bonds is trigonal planar. Trigonal planar means a flat triangle. So just draw a triangle and it's flat on the piece of paper. Okay. When you have only 2 bonds, that's linear. That's basically a central atom with all 3 atoms in one line. So this is all 3 atoms in one line, something that looks like this, Y, X, and X. So there's only 2 bonds coming out of the central atom and nothing else, okay? And then you have also 3 bonds and 1 lone pair. Now, once you add in a lone pairs start to take up more space. And this that would have just 3 bonds compared to the trigonal planar. The trigonal pyramid is a low pyramid. This is a low pyramid. It's a base of 3 with, okay, so showing the base of 3, this is X as the central atom. The base of 3 has 1 bond that's in the plane of the paper, 1 bond coming out front. This is what this thicker arrow is, that's going out front, in front of your paper. And then you have a dashed line, and this is 1 bond going out back, behind the plane of the paper. So this is like the tripod base of the tall pyramid, but it doesn't have a top. And why does it not have a top? Because there's a lone pair sitting on top that you can't see. So I'll draw it in green. Oops, don't want to draw that in green. I'll draw this lone pair in green, which is sitting on top, but it's not represented as one of the bonds. Okay, so it forces the other three bonds downward to just have the base of 3 compared to the flat triangle. It would be just 3 bonds spaced out as far as possible while stuck to the central atom, but it is not a flat triangle. Okay, so now let's take a look at this one. When you have 2 bonds and 1 or 2 lone pairs, that's going to be bent or V-shaped. And that's the example of when you have water, this H2O. This is 2 bonds and 2 lone pairs. And that means that this is the bent shape. Okay. So then we got to go back to, where did these come from in the first place? These are the Lewis structures. So that was from the last lecture. The Lewis structures is a series of steps where you draw the Lewis structure by calculating the valence electrons from the periodic table family numbers. And then you make sure that every atom has the octet or duet rule fulfilled using those valence electrons. So you're redistributing valence electrons amongst the whole molecule to build a molecule shape that is called the Lewis structure. That's the 2-dimensional, the bonds to the central atom. So we did that, but we're going to add the Lewis structure for some more compounds. Okay, so this is one more note, is when you have only 2 atoms. So for instance, O2. So when you have only 2 atoms like O2, O2 is an oxygen that's double bonded to another oxygen. You don't have a central atom. So when there is no central atom, this is going to always be a linear shape. So this is molecules that have no central atom. And the reason is for having no central atom is because there are only 2 atoms. So you have to have 3 atoms or more to have a central atom and then kick into these VSEPR shapes. But when you have only 2 atoms, then it's just 2 things in space stuck together. That's always going to be a line. So that's called linear. You will notice that it's also similar to this linear shape. The linear shape that has a central atom, that's this linear shape. The central atom is X, and then there's 2 bonds coming out of it. That's also called linear because you have 3 things connected in one line. Okay, so let's go on to, when you're given the Lewis structure, the ones that we have already looked at are the methane. So we drew this last time, so I'm just going to copy this from last time. It was a carbon in the middle with 4 hydrogens. And then we also had drawn the oxygen gas, which is an oxygen with a double bond and 2 lone pairs above each oxygen. Actually, did I do that on the last one? Yes. Okay. And then we also had sulfur dioxide, which is a sulfur, and the oxygen on one side has a double bond and a 2 lone pairs, one above and below. So that's a double bond. And then a single bond with an oxygen, and then there's lone pairs on the oxygen. And then there's also one more lone pair on the central sulfur atom. So notice that those are lone pairs. There are lone pairs on the outer atoms, and there's also a lone pair on the central sulfur atom, which I'm going to circle in green. This is the central atom, and that central atom is what you're going to be focusing on, and the lone pairs only on the central atom. Okay, so this is the central atom, and that central atom has 8 electrons around it. So the double bond was formed in order to obey the octet rule while also using the correct number of valence electrons. That was that little trick where I had to erase 2 pairs and add a double bond in order to use the correct number of valence electrons. And then also adding this one that we had done last time, carbon dioxide is a carbon with an oxygen on one side to a double bond, and lone pairs above and below the oxygen, and then an oxygen on the other side with lone pairs above and below, and that's also a double bond. And there's the central atom is carbon here. Oops, don't do that, do this. Okay, so this is the central atom of carbon here. So just a review though of drawing the Lewis structure for the one that we have not done yet is the nitrate ion. So the nitrate ion is this chemical formula NO3 with a negative charge. So the NO3 negative charge, you want to first figure out the number of valence electrons. So calculate the total valence electrons using the family numbers. So the calculation of the total valence electrons is going to be nitrogen is in family 5A and oxygen is in family 6A. And then the -1 charge, you need to add 1. Okay, so nitrogen will have 5 from the nitrogen, but the oxygen will have 6 times 3 because there are 3 oxygens. And then the +1 charge, you have to add 1 electron. Okay, so the negative charge means there's an extra electron. So adding all this up, there's going to be 18 plus 5 is 23 plus 1 is 24 total valence electrons. So next, that's the total valence electrons from those family numbers. And then you got to choose a central atom. So the central atom should be something that can form more than one bond and also allow for some symmetry. So between nitrogen and oxygen, both of them can form more than one bond, but nitrogen is the better choice because you could put nitrogen in the middle and then have some symmetry where you have oxygens around it. So this is 3 oxygens around it because there's 3 from the chemical formula. Then you want to add electrons to the outer atoms so that each atom has the octet rule fulfilled. Okay, so that's 1. Here's 2, and here's 3. So each of those oxygens has the octet rule fulfilled. There are a total of 8 electrons around each oxygen when you include the electrons in the bond. So this is 2 electrons in that bond, 2 electrons in that bond, 2 electrons in that bond. But the central atom, the nitrogen in the middle, also needs to have 8 electrons. So I'm going to add 2 more electrons on the nitrogen. So that will be a total of 8. So all those greens are showing some electrons are shared in those bonds. And then there's also a lone pair. Now let's make sure I use the correct total though. So doing this circling, I have 8 electrons here. Oops, don't do that. These move around on here. Okay, let me move this. Try this a different way. Nope, doesn't want to do this. Okay, I got to move those electrons because they're in the way. Come on, come on, come on, come on. All right, there we go. I'm erasing these green electrons because this iPad has a little bit of a glitch that when this moves, okay, that's better. Sorry, when the iPad gets to the very bottom, okay, do this. It has this ghost effect. Okay, so going back to what I was doing is I wanted to make sure that every atom has 8 electrons around it. So I draw a circle around 8, including the ones around that are included in the shared electrons that are bonds. So those are oxygens. Each of those have 8 electrons. The central nitrogen also has 8 electrons. But then I want to count how many electrons I used. So you go in and you literally, you count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I used 26 electrons. That's too many. So what do you do when you use too many? You need to erase 2 pairs and then form a double bond. So erasing 2 pairs, you can choose to erase 2 pairs from 2 atoms that are bonded together already. So don't just erase any 2 pairs. Erase a pair from one atom and then a pair from a different atom and then join those 2 atoms with that double bond. So I'm going to erase by showing you exactly what I'm going to erase in red. I'm going to erase a pair from an oxygen. It can be the one on the right, the one on the bottom, or the one on the left, but choose one oxygen to erase 2 electrons. That's one pair. And then this pair on the nitrogen gets erased. So erase 2 pairs and then form that double bond. And that's going to be this new double bond in red. Okay, so let me erase those now. I'm going to erase those X's and those electrons. And you will see that this double bond has the electrons in the bond are 4. And so the octet rule is still obeyed for the oxygen on the right. And the octet rule is still obeyed for the nitrogen in the middle. So this erasing 2 pairs and adding the double bond still allows for the octet rule to be fulfilled. Okay, so each atom still has the 8 electrons and you have used 2 less. You go and count them and you'll find that you've used 2 less electrons or 24 electrons, and that matches the total. So when every atom has the octet rule fulfilled and you've used the correct total, then you have the Lewis structure there. You have to do that to the nitrogen. It's because when you erase 2 pairs, you are allowing for the octet to still be fulfilled. You cannot have more than 8 electrons. So if you left the lone pair on the nitrogen, that would have 10 electrons on there. And you can't have more than 8. You can't have less than 8. You need to have 8. Sound good? Okay, so let's go back. Now, every atom has a Lewis structure, or sorry, every molecule has a Lewis structure, and you want to then look at the lone pairs and bonds on the central atom. So that's this process to determine the VSEPR shape. You look at the central atom and figure out how many bonds and how many lone pairs. So this is the central atom is carbon, and this central atom has 4 bonds on it. So they happen to be single bonds, but there are 4 lines coming out of here. 1, 2, 3, 4. So 4 bonds is the recipe for tetrahedral. So that's the tetrahedral VSEPR shape. And that tetrahedral VSEPR shape, redrawing this, is the pyramid. I wanted that to be in purple, but I'm going to do this in purple, where you have a central atom. That's your carbon, which is typically going to be black, actually. So that's your carbon. And then you've got 1 hydrogen, which are white, and 1 hydrogen above and 1 hydrogen also at an angle to the left. Then you also have 1 hydrogen in the plane of the paper. So that's this one to the left. And then you have 1 hydrogen coming out front. That's that thicker line. That's going out front. That's that thick line, that triangle. And then you have the dashed line, and this is going out back. And that uses the 3-dimensional space so that all of those bonds can space out in 3 dimensions and yet still be stuck to the central atom. So that's the tall pyramid. That's the base of 3 with a tall top. That's called tetrahedral. So next one is your oxygen gas. So oxygen gas is 2 oxygen atoms, and they are only 2 atoms. So this is 2 atoms bonded, but it is a double bond. And that is okay, because a double bond really just means a bond. So whether you're talking about a single bond, a double bond, or a triple bond, when you're referring to the 3-dimensional VSEPR shape, it doesn't matter if it's single, double, or triple. They are all just a bond. Okay, so how many bonds, how many lone pairs, that just uses the word bond. It actually doesn't matter if it's a single, double, or triple. And we'll see that in the next example. But this double bond is like a single bond. It's like a thick bond, but it's thicker. So it's a thicker bond or thicker connection between those 2 atoms. So whether it's a double bond or a triple bond, that doesn't mean they're going in 2 different directions or 3 different directions. It just means it's a thicker connection between those 2 atoms, filling that in. So the VSEPR shape when you have 2 atoms bonded is just linear. And so it's really just two oxygens bonded together very, very strongly in the double. This compares to the sulfur dioxide. So here's your central atom. And what you have on the central atom, the sulfur has one lone pair. You're definitely sure about that. So there's one lone pair. And there's also two bonds. And so this is what I mean about this is a single bond, and on the left side, there's a double bond. But when you can kind of fill that in like that, they're not, the double bond is not going in two different directions. So it is just one connection, which is the double bond. So you have the single bond and you have the double bond. Okay. So one lone pair and two bonds is the recipe for one lone pair and two bonds is the recipe for bent. So this is the bent shape. And to draw that bent shape, you have a sulfur in the middle. Okay, and sulfur is typically shown using yellow. So I'm going to fill that in with yellow. And then you have the bent shape of the oxygens, which are usually red. So this is a red oxygen and another red oxygen. And this is going to be bent. It's a downward V is what I'm drawing. So drawing the bonds in black. And the reason why it's bent, the reason why they're not trying to space out and be just one line is because you have some lone pairs, or that lone pair on the top takes up extra space. And it doesn't manifest, it's not, it affects the bent shape, but it is not actually drawn as part of the shape. Okay, so next one is carbon dioxide. So carbon dioxide, this is CO2, the central atom here has no lone pairs. So although there are lone pairs on the outer atoms, the central atom doesn't have any, but it has this double bond on the right, which is a bond, and this double bond on the left, which also is a bond. So there are two bonds. Okay, so even though they're double bonds, that counts as a same thing as calling it a bond. So what's the recipe for the one that has two bonds? That's this one, the linear shape. Okay, so to draw the linear shape, this is the linear shape. I'm going to have the carbon is typically shown as this black color, central atom. And then the bonds on either side are going to oxygens. Now you could draw that as a double bond or as just a thicker bond. I could actually do that for this one too. And then the oxygens I'm going to draw as red. Okay, so you've got the linear shape, and those are all in one line, all three atoms in one line. And then finally down to this one, the nitrate ion. This is the central atom is the nitrogen. So looking at that central atom, what is on it? There are three bonds. So you have 1, 2, and the double bond. So I'm going to have that double bond is one of those situations where you have not 4 bonds, because the double bond is a thicker line. Basically, it's a connection. So 3 bonds. What is the recipe for 3 bonds? Go back and look here. 3 bonds is the trigonal planar shape. So that's the trigonal planar. Trigonal planar is that flat triangle. So the flat triangle is where you have a central atom. This is the nitrogen. And then you have 3 bonds coming out of it. So this is 1, 2, and 3. One of them can be drawn as a double bond and thicker, but because of resonance, they actually all get to be eventually drawn as a thicker double bond. So this is 1, 2, 3. Nitrogen is usually shown using blue. So I'm going to give that a blue color here in the middle. And then the oxygens are usually drawn with the red color. So I'm going to, okay, that just did this whole shifting thing on me. So I've got to draw this further down. Sorry. I get another chance. So you've got 1, 2, 3 oxygens. And then you've got the central nitrogen in blue. Okay, and then you've got the bonds connecting those. Okay, that just jumped. I want to really get angry right now, but I can't do much about it. Okay, the central, don't jump again, please. Don't, it jumped. Okay. That's the triangle. That's the trigonal planar shape. So this is a flat triangle. I can draw boundaries around all of that, and that would be a flat triangle called trigonal planar. Okay. So we have the nitrogen and oxygen, N2 and O2. That's 99% of the air. These are not greenhouse gases, okay? But the other gases that are in the 1%, that includes argon, carbon dioxide, water vapor, methane, air pollutants, chlorofluorocarbons. That 1% does have some greenhouse gases, okay? So this one, carbon dioxide, CO2, that is a greenhouse gas. Water vapor, H2O, that is a greenhouse gas. This some of the air pollutants, not all of them, but ozone is an important one. These are greenhouse gases. And that is less than 1%. Okay, so that's less than 1%. And that's why we don't have to worry about the nitrogen and oxygen. They're the majority, more than the majority, right? 99%. But the ones that are greenhouse gases do have an effect. And here's why, is because the greenhouse gases, these are gases that trap heat. And exactly how these gases trap heat are in the molecule shapes, or specifically the bonds, okay? And so what happens is we have this natural energy balance, which is called the greenhouse effect. The sun sends energy, the earth reflects it out, and some of the energy that is sent to us from the sun is trapped in the atmosphere, and that's a good thing. That was established over millions of years. And this is what we have, though, is not the greenhouse effect in warming. We have the enhanced greenhouse effect because there are more and more of the greenhouse gases, not that we've had levels of carbon dioxide. Remember, going back 800,000 years, they're higher than they ever have been. So that's way less than the 1%. It's only in the parts per million, okay? But the carbon dioxide causes warming. And so this is when infrared hits a molecule. It is causing the molecule to vibrate, bend, or stretch. And so the vibrations, the molecular vibrations, are caused by infrared. And that's different from microwaves that cause certain molecules, specifically polar molecules. I know you don't know that yet, but we're going to get to those. Microwaves cause polar molecules like water to just rotate. And compared to UV, ultraviolet causes molecules to have their bonds broken. Okay, so but infrared causes molecules to vibrate, also bend or stretch. And the bending, stretching, and vibrating is really a temporary holding onto infrared energy, and that molecule holds onto it before that infrared can escape out to outer space. So that's the trapping of heat, is that infrared comes in from the sun and it would naturally just bounce off and go back out into outer space. But the greenhouse effect keeps it in the atmosphere because the gases hold on to it before it can bounce way back out. Okay, so when we have the molecule shapes, we can try to understand how these absorb infrared heat. So we have the Lewis structure of carbon dioxide is this carbon with a double bond on either side. Now I'm not going to draw the other lone pairs on the oxygens because I'm focusing on the VSEPR shape, which is linear. So this is a linear VSEPR shape. And this linear VSEPR shape can absorb infrared. And what happens is, I showed you in the video, this can bend or stretch. It can bend, it can stretch. It can also vibrate. But in the vibration, the main vibrations that absorb infrared are bending and stretching. Okay, and so because it can bend and stretch, that makes it a greenhouse gas. And how does it bend and stretch? It's a shape that is linear that can then bend as a V, and that will temporarily hold the infrared energy, and then it'll go snap back to the linear shape. And then that, when it snaps back, the infrared that was absorbed is released to the atmosphere. Okay, ozone is this Lewis structure with an oxygen in the middle, a double bond on one side and a single bond on the other side, and there's a lone pair on the central atom. So that's a bent shape. And what happens to this shape is that it is something that can form a more bent shape. So when this is hit with infrared, it can also bend and stretch. It can bend as a bent shape into a more bent shape, and it can also stretch. And when the molecule can bend and stretch, that means that this ozone is hit with infrared, and it can bend a little more. And in that stretched or stressed out, more bent shape, it has absorbed the infrared, but then it will return to its less bent shape, which is still bent. And when it returns, it releases that infrared heat energy into the atmosphere. So that makes it a greenhouse gas. The water vapor, moving this, is also an oxygen with the central atom having two bonds, and then there are two lone pairs. And that we saw the water vapor is a bent shape. So two bonds and two lone pairs is the bent shape. And this also does the same thing. When it's hit with infrared, it can bend and stretch. So even though it's already a bent shape, it can bend even more, or it can stretch. And that bending and stretching vibration, this absorbs infrared when it bends. And then when it returns to its less bent shape, it releases that infrared to the atmosphere. And that makes it a greenhouse gas. Then we've got methane. So methane is the carbon with 4 hydrogens, 1, 2, 3, 4. That's the tetrahedral shape. And this can absorb infrared. Every one of those bonds can bend a little bit, vibrate, stretch. This can also bend and stretch. And the bending and stretching means that infrared is absorbed. And when it returns to its natural, less bent or less stretched out shape, it releases infrared into the atmosphere, and that makes it a greenhouse gas. And this compares to oxygen gas and nitrogen gas. So oxygen is a double bond to another oxygen. It's a diatomic molecule, also called a molecular element, because it's only made out of one type of element. Nitrogen gas is 2 nitrogens that are bonded with a triple bond. Now, these are simple molecules. They're both diatomic and they're both only one element, but what makes them unique, and as far as gases in the atmosphere, is they are both linear with no central atom. And being linear with no central atom is basically just like being a pen. So have a pen and try to bend that pen. So hold that pen or pencil or whatever you're writing with and try to bend it. Can you bend that? No. This is different from this linear shape with the central atom. The carbon dioxide is linear with the central atom, and that's like having 2 pens, and you can bend that. Okay, so having 2 pens next to each other, linear with a central atom, you can bend. Linear with no central atom, you cannot bend. So these can't bend, and they also can't stretch. Go ahead and try to stretch that pen out. If you have a single pen, you can't pull that out. You cannot. And so since it cannot bend or stretch, this means that it is not going to absorb infrared. And because it does not absorb infrared, it's not a greenhouse gas, either of those molecules. As I mentioned, we have the next module we're going into. Module 5 is combustion reactions. And it's short. There's actually only 1 lecture. So this is an intro to combustion reactions, and we'll continue it in the next lecture. But this one is still part of today's, which is writing a combustion reaction and then balancing it. So this should be some review of writing chemical formulas when you're given a name, and also review of balancing using coefficients and trying to make the atoms equal on both sides for a chemical reaction. Okay, so a combustion reaction is a special reaction that is a hydrocarbon, generally going to be a hydrocarbon, and a hydrocarbon is only carbons and hydrogens. So the hydrocarbons that we'll see the most are called alkanes. Alkanes have the name ending ANE. So the name ending ANE means all single bonds between those carbons and hydrogens. Okay, so that's why it's called hydro for hydrogen and carbons. You only have hydrogens and carbons, and you also have only single bonds, as opposed to say double bonds, triple bonds. So the name ending is ANE. So this is the ANE name ending. We'll see later in a much later module that when you have double bonds or triple bonds, you end up changing a name ending for hydrocarbons. Okay, so but the general formula for this alkanes we saw in the video and you have here is the number of carbons is N. And then you can calculate, you can figure out how many hydrogens there are if you know that number of carbons, N. So say, for example, you have one carbon. So that means N is 1. Okay, so to figure out the number of hydrogens is equal to 2N plus 2. So if you have one carbon, that means this is going to be 2 times 1 plus 2, which is 4. So that means 4 hydrogens. And so that's how you get the chemical formula CH4. So you have the one carbon, which does not need a 1 subscript because just having the element symbol C is 1. Okay. And then the H has the subscript 4, which we calculated the number of hydrogens. If you know the number of carbons, you can calculate or determine the number of hydrogens. Now, the number of carbons is based on the prefix. So that's this next part, is the prefixes that we have seen before in writing chemical names for covalent compounds. They are the pentane is 5, hexane is 6, heptane is 7. But the first 4 are different. And this is this mnemonic, mother eats peanut butter, where mother is 1. That's methane. That's the prefix meth is 1 carbon. So that's CH4 that we just looked at that chemical formula. Ethane is the E, and that is 2 carbons. So the prefix is eth. And so this is C2. And then you can figure out how many hydrogens, which is going to be 2 times 2 plus 2, or 6. C2H6 is the chemical formula for ethane. And then propane. So the prefix prop is 3 carbons. So this is C3. And then the number of hydrogens is 3 times 2 plus 2 is 8. So C3H8. And then bute. So butane. Bute is the prefix for 4 carbons. So this is going to be C4. And then the number of hydrogens is going to be 4 times 2 plus 2, or 10 hydrogens. So C4H10 is the chemical formula for butane. And then this is a note, is that when you are balancing combustion reactions, you want to start by putting a 2 in front of the hydrocarbon. So I'm going to make sure you guys see that. And this is just a starting point. It's a suggestion. And so you balance the combustion reactions, which have a general form of you're always going to have a hydrocarbon. So we talked about the hydrocarbon. You're always going to have oxygen as a reactant. So that's O2. And that's a reactant, and that's on the left side. So you have the left side of the arrow and the right side of the arrow. And then the product side is always going to be the same. Okay, so you're always going to have, going back to here, oxygen is always a reactant, and carbon dioxide and water are always products. So you're always going to have CO2 and H2O on the right side. Those are the product side. Okay, so the products are on the right side. And so you have this general form of the combustion reaction, where you can see the O2 is the reactant on the left side of the arrow, and you have the CO2 and H2O on the right side. So what changes is that hydrocarbon. This number of carbons and hydrogens will be determined by the prefix of the name, and then you can calculate the hydrogens. And so this is when you balance these reactions, you're always going to put a 2 in front of the hydrocarbon. So you'll see that. But let's put these when you are given a problem that looks like this. Write the complete balanced equation of the combustion of ethane. So if you know it's a combustion reaction, that means you know 3 things. You know that you're going to have a hydrocarbon, okay? And the hydrocarbon is ethane. So ethane is the prefix eth, means 2 carbons. And so that means you can figure out the chemical formula is C2. And you can calculate the number of hydrogens. This would be 2 times 2 plus 2, or 6. So you have the hydrocarbon is always going to be burned in a combustion reaction. When they tell you the combustion reaction, we're going to see a lot of different combustion or burning of things. And so these are combustion of hydrocarbons, specifically combustion of hydrocarbons. Okay. So the other things you will need to know are that the rest of it is exactly the same. So you always have on the left side, you can put a plus sign and O2. Oxygen is always going to be on the left side. That's a reactant. And then you can write an arrow. And then on the other side, on the right side of the arrow, are always the same: carbon dioxide and water. So on the right side of the arrow, it doesn't matter if you write CO2 first or H2O first, as long as they're both on the right side of the arrow. Okay. Same thing for the left side. It doesn't matter if you write C2H6 first or O2 first, as long as they're both on the left side of the arrow. Okay. So you have the left side, which is different from the right side. And to balance this, I'm going to start by putting that 2 in front of the hydrocarbon. So I'm going to put a 2 in front of that C2H6. That's a starting point. And this is a good start because it will send you to the other side, which is the number of carbons is now 4. So this has 4 carbons because it's 2 times 2. So I'm going to need to put a 4 in front of here, in front of CO2, to have 4 carbons. This also, this 2 in front of the C2H6 affects the number of hydrogens. It's 2 times 6, or 12 hydrogens in C2H6. Okay, so that will need 12 hydrogens on the right side. So to get 12 hydrogens, you need to put a 6 in front of H2O. So that's 6 times 2 for 12 hydrogens. So then I'm going to add up the number of oxygens between both the CO2 and the H2O. So this is going to be 4 times 2, or 8 oxygens from CO2, and then plus the 6 oxygens from H2O. That's 14 oxygens total on the right side between CO2, which is 4 times 2, and 6 times 1. 14 oxygens means I'm going to need 14 oxygens on the left side. So to get that, it's going to be 7 times 2, or 14 oxygens from 7 times 2 for O2. So that is a balanced equation when all of the atoms are equal on both sides. Okay, so it starts with writing the chemical equation from the chemical formulas. So you have a combustion reaction again. This time it's propane. So the prop prefix in the mnemonic mother eats peanut butter is 3 carbons. 3 carbons means your chemical formula is C3. So to figure out the number of hydrogens, it's 3 times 2 plus 2, or H8. So this is propane. That's the C3H8 is the hydrocarbon that's being burned in the combustion reaction. So then the rest of it is the same. On the left side of the arrow, you need oxygen. So you're going to write O2, and then you need an arrow. And then on the right side of the arrow, you're going to need CO2 plus H2O. So it doesn't matter that with the order of the left side or the right side, but they just have to be on the other side, either sides of the arrow. So don't move anything around, and also don't change any subscripts. We saw this before with balancing reactions in general. Don't ever change any subscripts. You only add coefficients. So the starting point is start by putting a 2 in front of the hydrocarbon, which is a 2 in front of C3H8. So this means there's going to be 2 times 3 or 6 carbons. And there's also going to be 2 times 8 or 16 hydrogens. Okay, so to have the 6 carbons, I'm going to need to put a 6 over on the right side in front of CO2. That will give me 6 carbons. And then to have 16 hydrogens, I'm going to need to put an 8 in front of H2O. That's 8 times 2 for 16 hydrogens. Then I'm going to have to add those oxygens up from both CO2 and H2O. So that's 6 times 2 or 12 from CO2, and then 8 times 1 or 8 from H2O. That's 20 oxygens on the right side. So to get 20 oxygens on the left side, I'm going to put a 10 in front of O2, and that would be 20 oxygens. Okay.
Do you mind scrolling up, please?
Yeah.
Thank you.
So one thing you can do for this, which might be familiar to you, is that you can reduce. So you can reduce all of these because they all can be divided by a 2. So although you start by putting a 2 in front of the hydrocarbon, then you got to see if you can reduce everything. So this will end up being 1 and 5 and a 3 and a 4. So you can reduce, or you can divide all by 2. So if you can all divide all of them, not just 1 or 2 of them, when you can divide all by 2, that would be the final step. Okay. Why do you start with a 2 in front of the hydrocarbon? Because it is a starting point that makes things a lot easier, because you need a starting point. That's the best answer. It is a trick. You don't have to start with a 2 in front of the hydrogen, but it's a trick that will work about 50% of the time. Okay. Aside from you need a starting point somewhere, right? So that's my recommendation, is start with that. You might end with dividing everything by 2, but it is a trick that is why I highlighted this in green. Got it? So now let's take a look at the next one, which is the combustion of pentane. So pentane is pent. That prefix is 5. So this prefix is 5 carbons. So that means it's going to be C5. And then the number of hydrogens is 5 times 2 plus 2, or 12. So this is C5H12. And then the rest of it is the same. So this is O2. And then on the right side of the arrow, CO2 plus H2O. So you guys are with me on this. Start with putting a 2 in front of the hydrogen. Did I convince you, Alexa, that you should put a 2 in front of the hydrogen?
Yes.
Okay, I'm sorry, two in front of the hydrocarbon. It's a starting point, because really there's a lot of tricks in this one that are different from other balancing equations. Other balancing equations, you kind of start by just making an odd number even. But this one is a little bit trickier with the hydrocarbons. So putting a 2 in front of the hydrocarbon will give me 10 carbons and 24 hydrogens, which then moves me over to the right side. To get 10 carbons, I'm going to need to put a 10 in front of CO2, and that would be 10 carbons. And then I'm going to put a 12 in front of H2O, and that's going to be 12 times 2, or 24 hydrogens. Now I'm going to add those oxygens on the right side. So that's 10 times 2, or 20 from CO2, and 12 times 1, or 12 from H2O. So that's going to be 32 oxygens on the right side. So in order to get 32 oxygens on the left side, I'm going to need to put a 16. So that's going to be 16 times 2, or 32 oxygens on the left side. Okay, so because I can see that I can reduce these as well, I can divide all of these by 2. This will be a 1 and an 8 and a 5 and a 6. Okay. And so the numbers do get bigger, but they are still reasonable, okay? This is combustion of octane. So again, combustion reaction, we know that it's going to be oxygen. I'm actually going to start this differently. I'm going to start with, we know it's going to be O2 on the left and an arrow, and then CO2 and H2O on the right. Okay, but the hydrocarbon this time is octane. So oct is the metric, is not a metric prefix, sorry. Oct is the prefix for the hydrocarbon that is 8 carbons. So this means we're looking at C8. The number of hydrogens is going to be 8 times 2 plus 2, which is going to be 18. Okay, so C8H18 is the hydrocarbon. I left some space and put it at the front, but it doesn't have to be at the front. It could be second, it could be oxygen first, as long as it's on the left side of this arrow. So I'm going to start by putting a 2 in front of this C8H18, which means it's going to be 2 times 8 or 16 carbons. And then it's 2 times 18, which I'm actually going to need my calculator to do. So 2 times 18 is 36 hydrogens. And to have this equal on the other side, I need a 16 in front of CO2. So that's going to be 16 carbons. And then it's going to be 18 times 2 for 36 hydrogens. So then I'm going to add those oxygens from both CO2 and H2O. So that's 16 times 2 or 32. And plus the oxygens from H2O, that's 18 times 1 or 18. 32 plus 18 is 50 oxygens. So in order to get 50 oxygens over here, I need to put a 25 in front of O2, or 25 times 2 for 50 oxygens here. So these coefficients, I cannot divide by 2. And so this stays at 2, 25, 16, and 18.